The third problem we'll work together from our Chapter 16 Round 1 test has us calculate the pH of a solution formed when 2.5 grams of lithium oxide dissolves in 1.5 liters of solution. Lithium oxide, a metal oxide, when placed in water, forms a basic solution. Let's keep in mind the chemistry as we decide the value given for the concentration of our base. When a metal oxide gets placed into water, our pattern of chemistry says it does indeed form an Arrhenius base known as lithium hydroxide, but keep in mind the balanced equation. You can even think of this in terms of a net ionic equation. When oxide ion combines with water, it indeed forms 2 units of hydroxide ion. When we begin our problem, we have to consider 2 base ions that are being formed for every 1 mole's worth of our salt, lithium oxide. We'll go to work using a little molar mass conversion from grams into mole. Given 2.5 grams of our compound, Li2O, we'll place that over its molar mass of 30 grams per mole and divide that by the new volume, 1.5 liters. Grams over molar mass per liter of solution gives us the molarity 0.056 molar. But remember, the stoichiometry shows if the lithium oxide, 0.056 molar, would need to be doubled to get the concentration then of the base ions OH negative. Knowing that we have base ions, we hit negative log of 0.056 times 2 to get something known as POH, and then we simply subtract 14 from that answer. The POH I found 0.9542, carrying plenty of decimals. So flipping that into a pH, we find 13.05 pH units for this strong base. The trick I think here was forgetting that the base ion hydroxide is produced to the value of 2, a stoichiometric ratio of 1 to 2. Let's also tackle the last problem on our most missed questions from our first round of testing. We're being asked to calculate the value of hydroxide for the pH of the solution that is a mixture of sodium acetate as well as barium acetate. Given 2 different salts, we are now looking at calculating the pH of a solution. I'm noticing that there's a common ion here between the 2. As I think through the chemistry, I'm seeing sodium acetate written as NaC2H3O2. Its concentration 0.045 molar. And we have a 0.55 molar barium acetate. Barium is a +2, acetate with its -1. We end up having 2 units of the acetate. And if we have 0.55 molar, we actually have twice that value of the acetate ion. So to think about the chemistry of this hydrolysis reaction, notice that these are salts. They are not acid, not base, and the first name of both belong to strong parent bases. The ion that we're interested in is the acetate ion as it undergoes the process of hydrolysis, grabbing back the proton from water to create its conjugate acid, acetic acid, and leaving the solution basic, OH negative. Salts with anions of weak parent acids, such as the acetate ion, hydrolyze to produce a basic solution. We need to work out the initial concentration of the acetate ion by considering the 2 solutions added together. If the sodium acetate contributed 0.045 molar of the acetate ion, and the barium acetate contributed 0.55 molar times 2 for the 2 units of acetate, we have to consider adding those values together to find the new total molarity of the anion called acetate. When I add those together, I find 0.045 plus 0.55 times 2, and I'll hit to be sure. Oh, here I'm noticing that on our test it is written as 0.055 molar, and when I retyped the question I had 0.55. I'd like to match the test, so with your forgiveness I'm going to fix that typo, and I'm glad I caught it before I went too far. We will modify the question as is written to be 055 so it indeed matches the test answers, so you can correctly correct the test that was given. So 0.055 doubled plus 0.045 gives us a new value of 0.155 molar, the initial concentration there of the acetate ion. We also need to consider a Kb value for this expression. The acetate created a basic solution. I have to find the value of a Ka for acetic acid and convert it into a Kb for the expression that we've written. I know that acetic acid has a value of 1.8 times 10 to the negative fifth for its Ka value. We can easily convert a Ka into a Kb knowing the ion product constant for water, which we know to be 1 times 10 to the negative 14th. Kw divided by Ka gives us the value of Kb, and when I hit that, I found 5.56 times 10 to the negative 10th, our Kb expression for the hydrolysis of our acetate ion. Using the Kb, we'll set that equal to the value of the ions, which are both valued at x, so I'll square x, over the total concentration, 0.155 molar. I'll cross multiply and square root to find the value of x, knowing that we let x stand for the concentration of hydroxide ions, OH negative. And when I solved, I found 9.28 times 10 to the negative 6th molar units. This is indeed a base, so when we negative log 9.28 times 10 to the negative 6, we get something called POH, and 14 minus my answer gives me the pH value of 8.97.